Alrighty, gang, welcome back. Today we're going to kind of finish developing our synthetic division techniques for factoring, and we're going to get a lot of practice with it. So I'm going to show you, what's it? You remember the second to last problem we did on Tuesday, right? Where we had to factor a polynomial using synthetic division. Came with a little hint, right? Came with a little hint saying that P of 1 is 0, right? That we think 1 is a root. Today we're going to do more of the same, but instead of providing those hints, I'm going to show you kind of how to come up with them. And then we'll run through that same algorithm. We'll get lots of practice. All right. So let me get this stuff out of the way. Some fresh paper. And then we get cooking. All right, here we are. So this of course is MAC1140, the section number 009. It is a pre-calculus class. And today is the 7th of October, 2021. Today we're looking at the section in the textbook titled Real Zeros, aka roots of polynomials. For anybody reading along, there's some stuff in this section that I'm not going to go over with you guys. I'm going to keep it kind of simple and focused to make sure that you develop the skills in the area where we really need them. What else do I want to say here at the start? Well, I guess not much. So maybe recall. Any polynomial can be written in two forms. Your book calls these the expanded form and the factored form. And the thing I wanted to kind of remind you or demonstrate to you is that regardless of the form you're in, so for example, maybe P of X is 2x cubed minus 2x squared minus 28x plus 48, whose factored form would be 2 times x minus 2 times x minus 3 times x plus 4. The thing I wanted to remind you is that the lead coefficient here in the expanded form and the lead coefficient here in the factored form are the same. So you recall the very last problem we did on Tuesday, where I asked you to come up with a polynomial given the roots. So I told you, find me a polynomial that has this set of roots, and then also having the coefficient of x cubed equal to -6. That last bit of information is what we needed in order to calculate the lead coefficient. And that lead coefficient is the same whether you're in the factored form or the expanded form. That can be a useful tool. So if you're given the expanded form and you want to write down the factored form, all you need are the roots. Conversely, if you're given the roots and the lead coefficient, you can easily write down the factored form. So the big deal here is, of course, that the roots and the factors are kind of equivalent. If you know the roots, then you know the factors. If you know the factors, then you know the roots. The only additional thing you need, if you know the roots, to uniquely determine your polynomial is the lead coefficient. Okay. So last time we talked about how to draw the graph of a polynomial. We've been talking about this for a while now. If I give you a polynomial in its expanded form and I ask you to draw the graph, you need to put it into the factored form. And then from the factored form, you can find the roots, like this guy would have roots 2, 3, and -4. Their multiplicities, in this case, they're all 1. That'll tell you the local behavior near the roots. And then the expanded form will tell you the end behavior. So this is a positive lead coefficient with degree 3. So we could draw the graph just using the end behavior from this and the local behavior near the roots from this. The challenge, of course, is going from the expanded form to the factored form. Factoring quadratics is pretty easy. You know, you can use the AC method, or if that doesn't work, you can use the quadratic formula. But we're never going to get stuck on a quadratic. We can always factor a quadratic. The problem is with a degree 3 or larger polynomial, we need some other tools. We've seen how if you know what to divide by, you can factor something like this using synthetic division. The trick is figuring out what to divide by. In other words, the trick is coming up with some numbers which you think might be roots, some numbers which you think might tell you the factors, or at least one factor to get you started. If the problem doesn't tell you, hint, try dividing by x minus 1, or hint, p of 2 is 0, then you need to come up with that on your own. And the tool we have for coming up with that is called the rational roots theorem. And I have a funny story to go along with this rational roots theorem. Hopefully I'll remember to tell it. So what the rational roots theorem says is if the polynomial p of x equals an x to the n plus an minus 1 x to the n minus 1 plus all the way down to a1 x plus a0, if this kind of general expanded form polynomial has any rational roots, then they must be of the form x equals plus or minus little p over little q. Sorry, this you can't see that. This is a p. Sorry, this pen. X equals plus or minus p over q, where p divides the constant term a0 and q divides the lead coefficient an. So what this theorem does is looking at the expanded form of a polynomial gives you a way of coming up with a list of numbers that might be roots. And then you can test them one at a time using synthetic division. If you're wondering kind of why this is true, I invite you to imagine multiplying this thing out. So if I were to multiply x minus 2 times x minus 3 times x plus 4, the constant term from all of that would be 2 times 3 times 4, or I guess -2 times -3 times 4. Notice that each one of those numbers is a divisor of 48. In fact, it's 24, which times 2 is 48. So the product of the roots has to be the constant term, or at least the product of the roots and the lead coefficient has to be the constant term, which means any root of this polynomial will automatically be a divisor of 48. Now, there are other divisors of 48, right? 24 is a divisor of 48, 8 is a divisor of 48, 12 is a divisor of 48, and none of those are roots. But 2 divides 48, 3 divides 48, and 4 divides 48. And that's not a coincidence. And that's exactly what this theorem is saying. If you want to know more about these sort of things, you can look up Vieta's formulas. This is a consequence of Vieta's formulas for polynomial roots. Pretty cool stuff. But for us, this is going to be good enough to let us factor pretty much anything that we would ever want to factor. Okay. So how do we use it? I give you a polynomial, and I say factor this thing and graph it. You use this rational roots theorem to come up with a list of possible rational roots. Then, using synthetic division, you check them one at a time. As soon as you find a root, because you're checking with synthetic division, you will also find the quotient polynomial. So you'll get a factor and the quotient polynomial. And then you start back over on that quotient polynomial. Oh, thank you, Sarah. Yeah, I'm a little bit behind on uploading the MAC1140 lectures. I'll try to get those all up this afternoon. All right, so let's see if we can do this. Let's factor and graph the polynomial p of x equals 2x cubed plus x squared minus 13x plus 6. And the trick is to use the rational roots theorem and synthetic division. So the rational roots theorem says come up with your P's and Q's. Come up with your divisors of the constant term and divisors of the lead coefficient. So my P's here are the divisors of 6. What numbers divide 6? Genuinely asking. What are the, I just want to make sure we're on the same page with what we mean by divides. So what are the divisors of 6? Anybody?
2 and 3.
2 and 3, good. There's 2 others. So any number is divisible by itself. And then, yep, 6, 3, and 2. And then any number is also divisible by 1. So my full list of divisors of 6, the numbers that cleanly go into 6, are 6, 3, 2, and 1. And then the divisors of 2, because 2 is prime numbers are divisible only by themselves and 1. So this means that my possible rational roots, we have to take every fraction where the numerator comes from this list and the denominator comes from this list, right? Possible P's over Q's, and we have to include the plus and minus. So here's how I do this. I start with everything from here over 1. So I'd say that's plus minus 6 over 1, plus minus 3 over 1, plus minus 2 over 1, and plus minus 1 over 1. Then we also have to take all of these over 2. So that's plus minus 6 over 2, plus minus 3 over 2, plus minus 2 over 2, and plus minus 1 over 2. And some of these are redundant, right? Some numbers show up more than once on this list, like 6 over 2 is 3. So I'm just going to cross that off. 2 over 2 is 1. So I'm going to cross that off. And I think that's everything, right? Nothing else is showing up twice. So how many things do we have to check here? I've got 1, 2, 3, 4, 5, 6 guys, all with plus and minus. So there's a possible 12 things I need to check. Now we're not going to check all 12. As soon as you find one that works, you stop, write down the quotient polynomial, and you start over with that thing. And if you're lucky, you'll find one pretty quickly. And if you're luckier still, the quotient polynomial will be something we can factor easily. But this is where we begin. So we come up with our list of possible rational roots according to the theorem. And then we start testing things from that list using synthetic division. So I'm going to start by testing x equals 1. In other words, I'm going to divide p of x by x minus 1. All right, because x minus 1 is the factor that would give me a root at 1. And the way we do that synthetic division, I write the 1 here, right? Dividing by x minus c, you just write c. And then you write the coefficients of p, which are 2, 1, negative 13, and positive 6. And then we do the synthetic division. So I bring down the 2. 1 times 2 is 2. 2 plus 1 is 3. 1 times 3 is 3. Negative 13 plus 3 is negative 10. 1 times negative 10 is negative 10. Plus 6 is negative 4. So is 1 a root?
No.
Good, yeah, no, it's not. So remember, by your remainder theorem, this remainder is negative 4 is equal to p of 1. So x equals 1 is not a root. So what we're looking for is the remainder to come out to 0, right? Because then p of that thing would be 0, which is what it means to be a root. So this guy didn't work. So we move on to the next thing. Next, I would just test 2. And people often ask me, can't I test these just by plugging in to the polynomial? The answer there is yes. You could test to see if these numbers are roots by plugging in, but that wouldn't tell you the quotient polynomial. So the nice thing about synthetic division, first off, it's faster than plugging numbers into this because you don't have to raise anything to any powers. Secondly, it gives you the factors. It not only tells you, okay, yeah, this thing is a factor because that number is a root, it gives you the other piece also, and that's the most important part. Okay, so let's test 2. Means I write down 2, and then the coefficients, which are 2, 1, negative 13, and 6. Bring down the 2. 2 times 2 is 4. 1 plus 4 is 5. 2 times 5 is 10. Negative 13 plus 10 is negative 3. 2 times negative 3 is negative 6. Hey, this time we got the 0. Oops, sorry, down here. So here my remainder is 0. So p of 2 is 0 by the remainder theorem, which means x equals 2 is a root, which means x minus 2 is a factor. And if you take this division and you write out the result in the form p equals qd plus r, now we write p of x equals q of x times d of x plus r of x. R, that remainder, is 0. So you'll just have p of x equals q of x times d of x, which means you've started to factor, right? If I write this out, this says 2x cubed plus x squared minus 13x plus 6 is equal to the quotient polynomial 2x squared plus 5x minus 3 times the thing you just divided by, which was x minus 2. And you see, this really is the start of factoring. I was able to go from this cubic polynomial to a quadratic times a linear. I've begun factoring. I found this factor. And the important part is, from the synthetic division, I also found this quotient. So to finish what I'm doing here, to fully factor this and then graph it, I need to factor this quadratic. And you don't need to use the rational roots theorem for that. We know how to factor quadratics. Those are easier. So now we want to factor 2x squared plus 5x minus 3. And I would use the AC method for this. So here, a times c is 2 times negative 3 is negative 6. B, the middle term, is 5. So I need to come up with two numbers that multiply to negative 6 and add up to 5. Those would be positive 6 and negative 1. So I rewrite this as 2x squared plus 6x minus 1x minus 3. And then I factor by grouping. I can pull a 2x out from the first group, and I'm left with x plus 3. I can pull a minus 1 out from the second group, and I also am left with x plus 3 then. So I can factor the common term, x plus 3, out, and what's left is 2x minus 1. So I have 2x minus 1 times x plus 3. That's just factoring that quadratic. Which means my polynomial is 2x minus 1 times x plus 3 times x minus 2. And this would be an acceptable answer. If you gave me this as your answer, I would say that's fine. But it's not quite in the factored form that we talked about above, right? I said the lead coefficient should be the same, whether you're in the expanded form or the factored form. Here, the expanded form has a lead coefficient of 2. Here, I don't have any constant out front. And that's because this term right here has a 2x, and you can force that 2 out. So if I force factor out that 2, I get x minus 1/2 times x plus 3 times x minus 2. And now this is really in that fully factored form, although I would accept either of the two bottom things as your answer. Any questions on what we did here, how we arrive at this bottom purple line? Okay, we did say we want to draw the graph, so let's draw the graph. For the graph, I need the end behavior and the local behavior near the roots. So since we just factored, let's go ahead and write down the local behavior near the roots. My roots are positive 1/2, negative 3, and positive 2, and their multiplicities. Remember, multiplicity is the power of the factor. Each one of these is just a multiplicity of 1, right? Each one of these factors has exponent 1. So each one of these has multiplicity 1. The other thing I need is the end behavior. which I get by looking at the degree and the lead coefficient. So the degree is 3, which is odd. And the lead coefficient is 2, which is positive. So my end behavior is this. As x goes to negative infinity, y goes to negative infinity. And as x goes to positive infinity, y goes to positive infinity. Right, that's the end behavior associated with a odd degree and positive lead coefficient. So now I'm ready to draw my graph. First, I'll just come in here and plot the roots. -3, okay, so 1, 2, 3, here's -3. Positive 1/2, so if here's 1, then here's positive 1/2. And positive 2, which would be out here. So I've got my roots. My end behavior, we're going down on the left and up on the right. And now I can use that to stitch in the local behavior near the roots. I know that at -3, I've got a multiplicity 1 root, so either I'm crossing like this or like this. Because this end behavior is coming up from below, I know it has to be like this. And that means I'm leaving here going up, so I have to come back through here like this. And that means I'm coming back this way from below, so I have to go across here like this. And that's it. Now I'm ready to connect these pieces. And that's a fine graph. This would be the graph y equals p of x. Again, I may not know how tall this hill is. I may not know how deep this valley is, but I know that I have one local max and one local min. I know that I've got these 3 x-intercepts and that we cross like this at each of them. And I know my end behavior. So this is a really good graph, 10 out of 10. We can check our work in Desmos. So Desmos here, I want to graph p of x equals 2x cubed plus x squared minus 13x plus 6. And yeah, sure enough, looks pretty damn good. We can verify that I've got a root at -3. I've got a root at 0.5 or positive 1/2, and I've got a root at 2. Exactly like we said. I would be very happy with this graph first. In calculus, you're going to learn how to find exactly the point here. You're going to learn how to find exactly what this max is, the x value. That will require something called a derivative. And you'll be able to find this x value using the derivative, that tool from calculus. And then you would plug those in to find the y values. So while we might not know this yet, you'll be able to find it next semester. And that'll be an exciting step for y'all. Any questions on how I got this graph? Okay, let's try another one. We just did that. So this next guy is going to be a little bit more involved, and this time we'll just try to factor it. So P of x, my polynomial here, is going to be x to the 4 minus 5x cubed minus 5x squared plus 23x plus 10. And we could graph this also, but I want to get 2 more problems. So we're just going to try to factor this. As in the previous one, we're going to use the rational roots theorem. Which says we got to come up with our P's and our Q's. P's are going to be divisors of 10. Q's are going to be divisors of 1. Well, the numbers that cleanly divide 10 are 10, 5, 2, and 1. The numbers that cleanly divide 1 are just 1. So my possible rational roots, oh, this reminds me, I'll tell you that story. My possible rational roots are plus minus 10 over 1, plus minus 5 over 1, plus minus 2 over 1, plus minus 1 over 1. In other words, just plus minus 10, plus minus 5, plus minus 2, plus minus 1. All right, so fun story. I was really bad at factoring. Like in middle school and in high school, I was really bad at it. In fact, at the start of college, I was really bad at it. I failed Algebra 1, not once, not twice, but 3 times. Once in 8th grade, once in 9th grade, and once in 10th grade. And then I dropped the fuck out. Said, this just ain't for me. Not just of math, but out of school entirely. Later, in my mid-20s, I came back to college after working construction for a while and figuring I should probably get an education. I got really excited when I learned this rational roots theorem in pre-calculus class, because I was like, I always sucked at factoring. I still sucked at factoring at that point. And I was like, wow, finally, here's a tool, right? Here's a tool that will let me factor anything. So I went home all excited. I had a whiteboard on my wall at that time, and I just wrote down a random polynomial, right? I plucked out some coefficients and just made up a thing. And I went through the rational roots theorem, generated this big list of possible rational roots, and tested every single one of them with synthetic division. None of them worked. And I remember sitting around there. I had a friend of mine over, and sitting around there who's in the same class, scratching my head for quite a while, going, what the fuck? How is that possible? Is mathematics broken? Is there something wrong with the theorem? How is it possible that you test every number from the rational roots theorem, but none of them work? What must be true about the polynomial if none of the numbers from the rational roots theorem work?
That they irrational?
Yes, all of the roots were irrational. And it's a fun fact. Actually, I had a discussion with somebody about this the other day. If you randomly generate polynomials with integer coefficients between like -50 and 50, the probability that a given random polynomial will have any rational roots at all is about 5%. 95% of them will have no rational roots. So don't do what I did, right? Don't go writing down a random polynomial and think that you'll be able to factor it with this. It's not quite that powerful, because most polynomials don't have any rational roots. And of course, the problems that we're going to be using in class here are going to be chosen quite carefully, so that you have at least some rational roots, and that will allow you to get some work done. But it was very frustrating to me. I spent a whole afternoon on that. I was like, what the hell is going on? Eventually figured it out. Okay. So here, we need to test all of these guys, and I'm just going to start running through it. I'll test one first. That means I write a 1 here, and then the coefficients of p, which are 1, -5, -5, 23, and 10. Bring down the 1. 1 times 1 is 1. -5 plus 1 is -4. Times 1 is -4. plus -5 is -9, times 1 is -9, plus 23 is +14, times 1 is 14, plus 10 is 24. And since this is not 0, we know that x equals 1 is not a root. So we move on. All right. Well, what's the next thing I should try? Let's just try 2. So I write down my suspected root and the coefficients of p, which are 1, -5, -5, 23, and 10. And we try again. Oh, shit. Sorry. 2, 1, -5, -5, 23, and 10. There we go. All right. So I bring this down. 2 times 1 is 2. Plus -5 is -3. 2 times -3 is -6. Plus -5 is -11. 2 times -11 is -22. Plus +23 is 1. 2 times 1 is 2. Plus 10 is 12. So again, not equal to 0. So x equals 2 is not a root. Let's test 5 next. We'll just run through all the positive ones. So, okay, so I write 5 and then the coefficients 1, -5, -5, 23, and 10. Bring down the 1. 1 times 5 is 5. Plus -5 is 0. 5 times 0 is 0. Plus -5 is -5. Times +5 is -25. This looks good. Now it's -2. -2 times 5 is -10. Plus 10 is 0. All right. So this is equal to 0. So x equals 5 is a root, which means x minus 5 is a factor. And what's more, because I tested this not by plugging in, but by using synthetic division, in addition to learning that x equals 5 is a root, I also learned that this is the coefficients of the quotient polynomial. So I can say p of x is x minus 5, factor we found, times the quotient whose coefficients are here, which would be 1x cubed plus 0x squared minus 5x minus 2. Good so far? Okay, what do you notice is different between this problem and the last problem? The last problem, when we got to this step, we said, okay, we're going to continue factoring that thing. We want to do the same thing here, but something's a little different.
We don't have x squared.
Yeah, it certainly is true that there's not an x squared here, but even worse, there is an x cubed, right? Yeah, not a quadratic. So the thing that's left over, the factor that's left over after I pull out the x minus 5 factor, isn't something I can like factor by hand. So what should I do?
Synthetic division.
Right. Yep, we just keep doing more of the same. Now you can save yourself a bit of a headache by cooking up a new list for this guy. And this guy is going to have a smaller list than this guy. So the possible rational roots for this guy, you come up with his p's and his q's. So the p's here would be divisors of 2, which are just 2 and 1. And the q's for this guy are just 1. So his possible rational roots we only have to check plus minus 2 and plus minus 1. And it gets better. I've already tested x equals 1 and x equals 2. You see, if 1 was a root of this, then it would also have been a root of the original. And if 2 was a root of this, then it would have also been a root of the original. Since neither of them are roots of the original, neither of them could possibly be roots of this guy. So I only need to check -2 and -1 because I've already tested the 2 positive ones. So if I test -2, all right, -2, and then the coefficients of this new polynomial I'm working on, which are 1, 0, -5, and -2. Bring down the 1. -2 times 1 is -2, plus 0 is -2. -2 times -2 is +4, plus -5 is -1, times -2 is +2. Hey, we get a 0 here. Alrighty, so that tells me, since this is 0, we learn that x equals -2 is a root, which means x plus 2 is a factor. And also we have here the coefficients of the quotient. So I can continue writing the factored form of p of x. It's x minus 5 from before. Then this guy, the cubic, is x plus 2 times x squared minus 2x minus 1. And now I do have a quadratic. So now we're done with the synthetic division, right? Once you get down to a quadratic, you don't need to do any more synthetic division. We should try to factor that thing. X squared minus 2x minus 1. Well, if I want to factor that using my normal AC method, a times c here is -1, b here is -2. So I'm trying to come up with two numbers that multiply to -1, but add up to -2. Well, the only two numbers that multiply to -1 are 1 times -1, right? That's it. That's the only way to get two numbers that multiply, two integers, I should say two integers that multiply to -1. None of those don't add up to 2, right? You cannot make those add up to -2. So this quadratic doesn't factor nicely. And that means that his roots are not rational numbers. So another thought might be to try the rational roots theorem on that quadratic, since I don't see how to factor it. But if it doesn't factor with the AC method, then the roots aren't rational. That turns out to be an equivalence, right? So you have a quadratic has rational roots if and only if it can be factored by the AC method. So what should I do to factor this quadratic?
Use the quadratic formula.
Very good. The quadratic formula will tell me the roots of this guy. And then I know once I have the roots, I can write the factors. So we got to use the quadratic formula. I'll do it on another page. I'll write the quadratic formula here. It's -b plus or minus the square root of b squared minus 4ac all over 2a. Anytime you need a formula like this, it's good to write it down. It's a really great way to help you remember the formula. Don't just plug in right away. Write down the formula in general, then plug in. Just not necessary, but a little piece of advice. All right. So what are those numbers? Well, that's going to be -2 plus or minus the square root of b squared, which is 4, minus 4 times 1 times -1, all over 2a, which is going to be 2. So that's 2 plus minus the square root of 8 over 2. How do I simplify the square root of 8?
2 square root of 2.
Very good. Yeah, it's 2 root 2. Remember, 8 is 4 times 2. So the square root of 8 is the square root of 4 times the square root of 2. And the square root of 4 is 2. So this is 2 plus or minus 2 root 2 over 2. And you can factor a 2 out in the top, and you get 1 plus or minus the square root of 2 over 2. Cancel the 2's, and you get 1 plus minus root 2. So the roots of that quadratic are the two numbers 1 plus the square root of 2 and 1 minus the square root of 2. Which means my polynomial is x minus 5 times x plus 2 times x minus 1 plus square root of 2 times x minus 1 minus the square root of 2. Now a fun fact, root 2 is approximately 1.4. All right, that's a rough approximation. Root 2 is an irrational number, but it's useful to know about how big these are, right? If you wanted to graph this, I would need to know where to put these roots. So I'll just make a little note here that this is, if root 2 is 1.4, then 1 plus that is about 2.4. And 1 minus that is about -0.4. So if I were to look at the graph of this polynomial, I expect to see the following. I expect to see a root at 2.4, -0.4, -2, and +5. Let's see what we get. I'll put the expanded form into Desmos. P of x was, where is it? X to the 4. X to the 4 minus 5x cubed plus, or minus 5x squared plus 23x plus 10. And let's see what we have here. I have a root at -2. That's coming from this factor. I have a root at -0.414. That's coming from this factor, right? We said this is about -0.4. -0.4. I have a root over here at +2.414. That's this guy coming from this factor. And then I have the factor x minus 5 giving me that root at 5. So this is very good. We nailed it. And we could have drawn this graph, right? We could have drawn this graph, no problem. Find the end behavior, local behavior near the roots, and stitch everything together. We would be Gucci. And this one's a little more complicated than the last one, but this is about as bad as these get, right? You use synthetic division however many times is necessary until you get down to a quadratic. And once you're down to a quadratic, we can always handle it. Worst case scenario, use the quadratic formula. Are there any questions about what we did here? Okay, I'll say just one more thing, and that's that these little parentheses in here, these are important. Without these little parentheses, this wouldn't be correct. So as you work problems, make sure if you have a root that is kind of complicated like this, that when you write x minus that thing, you put that thing in some little parens. So you'd have like these double stacked parentheses for the whole factor. Okay. Your textbook talks about something called Descartes' rule of signs. I'm not going to beat you guys to death with that. It can be a little bit useful because it'll help you rule things out from your list, but it's not super useful. And I think it's more a source of confusion than anything. I want to stay focused on the stuff that you need in order to succeed in calculus. And Descartes' rule of signs ain't on that list. But if you want to learn about it, I invite you to. It is pretty cool. It's kind of a cute way of we should say like guessing at the number of positive roots. Okay, I want to factor two more, at least one more polynomial, and this next one's going to be a little scary. It's going to be degree 5. Did I talk to you guys about Évariste-Galois? Did we get to have that conversation?
I don't think so.
Oh, okay, yeah, let me tell you a fun story. So the next thing we're going to do, I'll go ahead and write down the problem first. So we're going to factor, and this time I will graph, factor and graph the polynomial p of x equals 2x to the 5 plus 5x to the 4 minus 8x cubed minus 14x squared plus 6x plus 9. The last problem we did, this was a degree 4 polynomial. And believe it or not, there is such a thing as, like the quadratic formula for a degree 2 polynomial. There is such a thing as a quartic formula for the degree 4 polynomial. It exists. I can show you. It's a little scary. Takes up several pages. Let's see, where is it? What we got? Here we go. Whoa! It's in here. You really can't see it there, can you? Let's see if we've got another option to display it. Web page. Here we go. This whole thing. You notice the scroll bar down here. So look at the top. You see this? Like the quadratic formula, but from hell. This is the quartic formula, or the general formula for the roots of a degree 4 polynomial in terms of the coefficients. Now, obviously, using this would be messier than what we did, right? Just trying to plug into this would take me all day. I can get this shit done pretty quickly. The next problem, we're looking at a degree 5 polynomial. There is a formula for degree 4 polynomials, just like there is for quadratics, and there's one for degree 3 polynomials. It's not quite as bad as what I just showed you. There is not and could not ever be a quintic formula, a formula for a degree 5 polynomial. Does not exist and cannot exist. And the man who discovered that was this young Frenchman named Évariste-Galois. Brilliant young man. You notice if you look at his dates of birth and death, he was living around the time of the French Revolution, just before, and he lived a very short life, 1811 to 1832. He died when he was 19. Brilliant young man, studied polynomial equations, also very passionate about politics, and he really wasn't well liked in his time. He was very outspoken and very intelligent, and the way he wrote his mathematics, even as a young man, the greatest mathematicians in the world at the time couldn't really understand what he was doing. He ended up founding a whole field of mathematics now called Galois theory. And one of the major results in Galois theory is called the Abel-Ruffini theorem, which says that there cannot exist ever a formula for the roots of a degree 5 polynomial in terms of like the regular algebra operations and the coefficients of the polynomial. the way he got there was by thinking about symmetries of graphs, right? Like even odd functions, stuff like that. Turns out cubic functions all have a certain kind of symmetry. Quartic functions all have a certain kind of symmetry. All of these polynomials have some sort of symmetries. They're complicated for higher degree polynomials, but they're out there. And by studying what are called permutations of the roots, kind of imagining switching the 5 and the 2, or switching this and this. By studying permutations of the roots, he was able to prove that based on certain algebraic structures called groups, group theory, that there could never ever be a formula for the roots of a degree 5 polynomial. So factoring something like this is even more intimidating, right? The degree 5 stuff and degree 4 stuff, degree 2 and 3 stuff, you can always get the answer using one of those formulas, as scary as they may be. But degree 5 stuff, you're really on your own. There are no formulas, even even scary big ones like the quartic formula. Tragically, Galois died at 19, and the story around his death is very, very sad. He got in a fight with some dude.
21, no?
I'm sorry?
21. I mean, if
Was
you.
he 21 when he died? 20, I'm sorry, age 20 when he died. I guess he was 19 when he came up with this stuff, so I apologize. Yeah, it would have been just before his 21st birthday, I guess, right? In May, a few months later, he would have turned 21. But he died very young, and in a duel, he got in a fight with a guy, and the guy challenged him to a duel, and back in the day, that was a thing. Galois accepted, and knowing full well that he was going to die, not expecting to survive the duel, the night before it, he sat down and wrote out all of his work on permutations of roots and the non-solvability of the quintic. It took several generations of mathematicians before it was well understood. That's how ahead of his time he was. And is just a beautiful story. There are a few books about him that are interesting and worth reading, and his mathematics, like I said, foundations of an entire field of math now called Galois theory. It's a subset of modern algebra, abstract algebra. If you enjoy polynomials and algebra, this is a good thing to shoot for down the road. But yeah, that's the story of Évariste Galois. Beautiful man, life cut tragically short, but managed to develop insane mathematics with very little formal training. So here's a degree 5 polynomial. This one can be factored, right? Not all of them can be. I mean, in theory, they all can be, but finding the roots can be incredibly hard. So this one, we're going to go ahead and try to find the roots. All right. I need to know what the rational roots theorem says. So I cook up my little p's and my little q's. Little p's would be divisors of 9, which are 9, 3, and 1. My little q's would be divisors of 2, which are 2 and 1. So my possible rational roots would be plus minus 9, plus minus 3, plus minus 1, plus minus 9 halves, and plus minus 3 halves. And we just start trying to factor, right? We just start testing these things. So I'll test 1. I'm going to write 1 and then 2, 5, negative 8, negative 14, 6, and 9.
Why we didn't take plus minus 9 halves?
I'm sorry, what was the?
So in possible roots, plus minus 9 halves also.
Oh, it's here. Yeah, 9 over 2.
Oh, sorry. I thought it's 1 half.
Oh, no. Yeah, this is a 9 halves. Oh, did I leave 1 half off? Yeah, 1 half should be there as well. I'm sorry. I did miss one. Sorry about that. Yes, 1 half should be there as well. All right. So I'm going to bring down this 2. 2 times 1 is 2. Plus 5 is 7. 1 times 7 is 7. plus -8 is -1 times +1 is -1 plus -14 is -15 times 1 is -15 plus 6 is, let's see, 6, 15, 6, 9, yeah, -9. Oh, good, and that times 1 is -9, and those summed to 0. All right, so 1 worked. Since my remainder is 0, we learned that x equals 1 is a root, which means x minus 1 is a factor. And that allows us to start factoring this thing. I would now say p of x is equal to x minus 1 times. I started with degree 5 divided by a degree 1. So these are going to be the coefficients of a degree 4 polynomial in order. 2x to the 4 plus 7x cubed minus 1x squared minus 15x minus 9. And you could, we would say, now we're going to start back over with this degree 4 polynomial. But because his constant term is -9 and his lead coefficient is 2, he's going to have the same list as the original, whose constant term was +9 and his lead coefficient is 2. So we don't need to cook up a new list. We just keep grinding on this guy. Let's do it. What would we like to check next? Let me allude to a possibility here. It is possible that 1 would work again, right? It's possible that there's another factor of x minus 1 in here. So let's check that. Let's see if I can rule 1 out. So I bring down the 2, 9, this would be +8, 8, and -15 and 8 is -7. 1 times -7 is -7, and this would be -16. Okay. So while 1 was a root of the original, it's not a root of this quotient. Right, 1 is a root of the original, and we factored out the x minus 1. We were checking to see if there was another factor of x minus 1 hiding in here, but the answer is no, because 1 is not a root of this guy. So now we can move past the 1s. The next thing I'm going to check, just to save time, because there's many things on this list, and I worked this out ahead of time, is 3/2. So I'll test x equals 3/2 next. And this lets us get some practice with fractions here. So I write 3/2, 2, 7, -1, -15, and -9, giving myself a little more space here because I know I'm going to have to do a bunch of arithmetic with fractions. We bring down the 2. 3/2 times 2 is 3. 7 and 3 is 10. 3/2 times 10, well, 10 is 2 times 5, so that's 3 times 5 is 15. 15 minus 1 is 14. 14 is 2 times 7, so this is the same as 3 times 7 is 21. -15 and 21 is 6. 3/2 times 6, 6 is 3 times 2, so that's 3 times 3, which is 9. And these do add to 0, so hey, that worked. So x equals 3/2 is a root, which means x minus 3/2 is a factor. So I can update my P of X. I now know that P of X is X minus 1 times X minus 3/2 times the quotient polynomial I get here, which would be 2x cubed plus 10x squared plus 14x plus 6. Some observations at this step. How do I factor anything I can do to help factor that quotient polynomial at the bottom now?
You can factor out a 2.
Yeah, and let's do that because this time the coefficients are different, right? The lead coefficient is still 2. This guy's a 6. So I would want to generate a fresh list of P's and Q's for this guy. And I can shrink that list down by factoring out any constants that come out. I'll bring the 2 all the way out front here because this is all being multiplied. Multiplication is commutative, so you can bring the 2 all the way out front. And what's going to be left here then is x cubed plus 5x squared plus 7x plus 3. And now I can generate a fresh list of P's and Q's for this guy. My P's are divisors of 3. 3 is prime, so that's just 3 and 1. My Q's are 1, so my possible roots are plus minus 3 and plus minus 1. And I've already factored out all the x minus 1 stuff that I can, right? We already tested 1, it worked. Then we tested 1 on the quotient that came out, it didn't work. So there are no further factors of x minus 1 in this thing. We found all of those. So we can skip the 1. Let's try negative 1. So I would write negative 1, and then the coefficients of this guy, which are 1, 5, 7, and 3. Bring this down. Negative 1 times 1 is negative 1, plus 5 is 4, times negative 1 is negative 4, plus 7 is 3, times negative 1 is negative 3, plus 3 is 0. Alrighty. So again, this is equal to 0. So x equals negative 1 is a root, which means x plus 1 is a factor. And I can update P of x. I now know P of x is 2 times x minus 1 times x minus 3/2 times x plus 1 times x squared plus 4x plus 3. And now that we've gotten down to a quadratic, we don't need to use any more synthetic division. Questions up to here? Okay. Is this easy to factor?
Yes, x plus 3, like in parentheses, and then x plus 1.
Very good. Yeah, I'm looking for two numbers whose product is 3 and sum is 4. Those are 3 and 1. So this is 2 times x minus 1 times x minus 3/2 times x plus 1 times x plus 1 times x plus 3. Is there anything else I could do with this to help me see what the graph will look like? Any other rewriting of this now?
Well, you can make x plus 1 squared
Right,
because it shows up twice.
exactly. X plus 1 times x plus 1 is x plus 1 squared, and that's going to tell me the multiplicity of the root at -1. So we have now done the very challenging thing. We have factored a degree 5 polynomial. And we know the roots and their multiplicities. X equals 1 is a root with multiplicity 1. X equals 3/2 is a root with multiplicity 1. X equals -1 is a root with multiplicity 2. And x equals -3 is a root with multiplicity 1. The other thing I need is the end behavior, which is easiest to see from the expanded form. Remember, the lead term here was 2x to the 5. So the end behavior, you could also see it from here, right? We talked about how to get end behavior from the factored form. Lead coefficient is 2, and the degree is 5. So the degree is odd. And the lead coefficient is 2, which is positive. So in that goes to notation, I would say as x goes to -infinity, y goes to -infinity, and as x goes to positive infinity, y will also go to positive infinity. In other words, my end behavior is down on the left, up on the right. And I have no idea what's going on in between here, but that's what we are going to figure out now. So taking these two pieces of information, I will draw a nice graph. Or as nice as I can. Start by plotting those roots. Let's see, -3, -1, 3/2 and 1. So over here, 1, 2, 3. This is -3. This is -1. And then we have 1. And also 3/2, which is 1.5. We'll add in our end behavior. We know we're going down on the left, and we know we're going up on the right. The root at -3 is multiplicity 1. And since I'm coming at it from below, it has to cross like this. Can't go like this, has to be like this. The root at -1 is multiplicity 2. So that's going to be a bounce. And it could either go from below to below or above to above. But since I'm coming through here, coming up, it has to be a above to above bounce. So I can say, okay, I've got this kind of parabolic behavior there. The other two roots are multiplicity 1. So I leave here going up. That means I got to come here going like this. And come here going like this. So then we stitch everything together. And there's your graph. Now again, is it perfect? No, probably not. Probably one of these hills is taller than the other. Probably this valley is either lower or very, very short. Hard to say for sure with the information that we have. Again, you'll get that in calculus, but this is a good graph. For a pre-calc graph of this function, this is excellent. And again, we can compare against Desmos. Before I pull up Desmos, any questions on where this graph came from? Remember, you will have to do this on a test. That test, by the way, we're getting pretty close to. So after we finish this section, I'm going to talk about complex numbers and complex roots to polynomials. After that, we're going to talk about rational functions. After that, we're going to talk about rational and polynomial inequalities, kind of revisiting that 1.8 stuff that we did at the very start of the term, but with, you know, a little bit more knowledge than we had before. After that, we'll be ready for the test. So any questions about where this graph's coming from? Okay, let's see what Desmos says. We had 2x to the 5 plus 5x to the 4 minus 8x to the 3 minus 14x to the 2 plus 6x plus 9. Damn, we're doing all right. Yeah, so okay, so this first hill is much taller. We couldn't have known that. This valley is kind of shallow. That's good. This guy, we're off a little bit on the peak there, but this is good. This is really good, right? Same basic shape, same end behavior, same local behavior near the roots, and most importantly, has the correct number of maxes, 1, 2 local maxes, has the correct number of mins, 1, 2 local mins, and they're all in the right relative position, right? Left to right, they're all showing up in the correct order. So this is, again, an awesome graph for us. This is a 10 out of 10 graph in this class. Last call for questions. Okay, then this is where we're going to leave it for today. I am going to open up a fresh homework set for you guys. Please start working on that. It'll be due on Tuesday, and it's going to be this stuff. And then Tuesday of next week, we're going to start working on complex numbers, complex roots of polynomials, and we'll be moving kind of into the rational function space from there. Again, the second exam is nearer than you think. It's not very far off. So make sure you're keeping up with the homework. I do have, I think, 50, at last check, 50 extension requests waiting for me in WebAssign. I saw that this morning. I'm going to go in there and clear those out before I open your new homework. So if you did need more time on any of those existing homework sets, please go ahead and submit that extension request as soon as you can. And that is it from me. All right. Tomorrow is Friday. I know we don't have class, but tomorrow is Friday. It's also the homecoming day for UF, which means the Santa Fe campus is closed. I am still going to have an office hour, but it's going to be a slightly weird office hour. It'll be at the same time. It'll be around 1 p.m. But I've got a student from one of my honors classes who's preparing to do a little student teaching thing. So I'll be working primarily with him. But if you do want to talk, you can come by. Just be aware that I'll be a little bit preoccupied with him until we get the basics sorted out there. And then, yeah, it's going to take me a minute to get through these. If you need more time on anything, go ahead and submit a request in WebAssign. I'll clear those out in a little bit. Yes, Soraya, thank you for the reminder. I'll go ahead and start uploading those lectures right now. Alrighty, is there anything else that I can do for you guys before we get scooching? Okay, then that's it. I hope you guys have a lovely rest of your day. If you need anything, Canvas message, email, Discord, you know the drill. Otherwise, I'll see y'all on Tuesday. Take good care.
Bye.
Bye.